Everybody, I'm doing a problem that's similar to this junior SMO review problem 2025, where they ask you to find the last three digits of this very lengthy alternating sum of squares. I cheaped out a little bit and just asked for the last two digits. You could actually, you can compute the entire value if you want to, the way this process goes. But one thing to notice real quickly is that you have the difference of two squares more or less repeating itself right here. So you got a little lemma here, but it's pretty well known right here. If you this is the difference of two squares, so you can write this as 1997, just the first one I'll do. Okay, plus 1996, and this is a quantity. I'm just doing the difference of two squares formula. So parenthetically 1997 plus 1996. Now here's where we get our money out of the difference of two squares. Now you have 1997. And this is why this is a junior problem. It's not particularly hard to notice this, but if you don't notice it, you're just stuck, really. Now 1997 minus 1996. So you see, we get lucky because this part right here is just one, right? 1997 minus 1996 is just one. So you're just left with 1997 plus, let me just write it out. You're just left with 1997. And the part that's slightly hard about this, I guess, is knowing just to leave it like this. There's no need to add it up. Plus 1996. Okay, like that. And if you see, this lemma more or less just does that abstractly. When you subtract the difference when the difference is just one between the integers, you're always going to get 2a plus 1. But you can write it as a plus 1 plus a, which is exactly this form. You see, a plus 1 plus a is exactly this form. Okay, so the alternating sum is very, very simple to manage. It's almost crazy looking, isn't it? It's like you just drop everything in the minus signs and it's just all the way across the same thing. But it's because of the algebra, okay? Now notice though, this is a triangular number. This is a famous triangular number, and this has a famous sum that's easy to show. This is equal to 1998. Remember, our goal is to find the last two digits. Times 1997. Over 2. All right. But isn't this 999? Times 1997? All right. Now we're asked to find the last two digits. So it's really enough right here just to multiply 99 times 97. And we'll go back to middle school here. 99 times 97, doing just the kind of the long multiplication right here. Okay, y'all, you get 693 when you do 7 times 99. And then when you do 9 times 99, you'll get, let's see, what do we get here? We get 0 right here, right? 9 times 99. Well, you got to place a 0 right here, right? Of course. All right, and then you get 9 times 9 is 81. So you have a 1 and a carry, but you don't even have to worry about this because remember how you just add these guys up, and so you would get 3, and then 9 plus 1 is 10. So that's it. The last two digits would be 03. Okay. 03 would be the last two digits of this sum. And if you think about this problem, it's a simple solution, but you're going, good God, how would you do this unless you see this? And this is very well known, the difference of two squares, but it's still kind of, if you just look at this, I went from here to here, where the squares went away and the minus signs went away. And then you go, really? So, and then of course that ended up being a triangular number sort of thing, okay? But the last two digits are, what I get, 03?